There is a horizon in space that no telescope will ever see past. Not because our instruments are too weak, or because the technology does not exist yet, but because the universe itself places a hard limit on what can be observed. A boundary built from the speed of light and the age of time. Beyond that boundary, space continues. Galaxies form and drift and age in regions that will remain forever invisible to us. Tonight, we will explore that boundary carefully and without rush. What it is, how it formed, what we believe lies beyond it, and why the answer to that last question may never change, no matter how far our science advances. Welcome to Sleepy Time Universe, where the biggest questions in science are explored at the pace of a calm and restful night. Tonight we will journey through each of these regions and explore the edge of what is known. If this sounds like the kind of content you return to, consider subscribing and leaving a comment below. What do you think lies beyond the farthest reach of the observable universe? Now let's begin. Chapter 1. The edge of what we know. We live inside a sphere of knowable space. It has a center, and that center is wherever you happen to be standing. Look in any direction, and you are looking into a region of the universe that light has had time to cross since the beginning of everything. Look far enough, and you reach the edge of that region. Beyond it, the universe continues. But its light has not yet reached us. It may never reach us. And so, for all practical purposes, everything beyond that boundary belongs to a universe we cannot access. This boundary is called the observable universe. It is not a wall. It is not a place where space ends or matter stops. It is simply the limit of what light, traveling at the fastest speed physics permits, has been able to cover in the time the universe has existed. The universe is approximately 13.8 billion years old. Light has been traveling since nearly the beginning. And yet, there are regions of space so distant that even their oldest light, sent out almost at the moment of creation, has still not arrived here. Understanding why requires sitting with a few ideas about how space and time work together. We will move through them slowly. The universe did not begin as a small point that exploded outward into empty space. It began as a condition, a state of extraordinarily high density and temperature that existed everywhere simultaneously. Space itself was born in that moment, and it has been expanding ever since. That expansion means that the universe we can observe today is not simply defined by how far light can travel in 13.8 billion years. It is defined by how far away the regions that emitted that ancient light have since moved, carried outward by the expansion of space itself. This is why the observable universe is 93 billion light-years in diameter, even though the universe is only 13.8 billion years old. The sources of the most distant light we can detect have been moving away from us for the entire history of the universe. By the time their light reaches us, those sources are vastly farther away than the distance their light has traveled. This distinction matters. It means the observable universe is not a fixed container. Its edge is defined by a combination of time, the speed of light, and the ongoing expansion of space. And as time passes, that edge shifts, though not always in the direction you might expect. For now, it is enough to settle into this picture. We sit at the center of a vast and luminous sphere of observable space. Beyond its edge, the universe continues in all directions, filled with matter and energy and structure that we have no means of detecting. We know it is there. We cannot see it. And the reasons for that invisibility are built into the deepest rules of how the universe operates. We will begin to examine those reasons now, moving outward from what we know, toward the boundary that defines the limit of everything we can ever hope to observe. Chapter 2. How far light has traveled. Light is the fastest thing in the universe. In a single second, it covers approximately 299,792 kilometers. In 1 year, it travels roughly 9.5 trillion kilometers. We call that distance a light year, not a measure of time, despite how it sounds, but a measure of the enormous distances between objects in space. When we look at the night sky, we are not seeing the universe as it is. We are seeing it as it was. The light entering your eyes from a distant star left that star years, decades, centuries, or even billions of years ago. You are looking back in time with every glance upward. The further away an object is, the older the light arriving from it, and the oldest light we can detect, the light that has been traveling the longest, defines the outer edge of everything we are able to observe. This is a simple idea with profound consequences. It means that seeing and knowing are not the same thing. We can see a galaxy 10 billion light years away, but what we are seeing is that galaxy as it existed 10 billion years ago. What it looks like today, we cannot say. It may have changed beyond recognition. It may have merged with neighboring galaxies, exhausted its star-forming gas, and grown quiet and dark. We are looking at a portrait of the past, not a window into the present. The universe has existed for approximately 13.8 billion years. In that time, light has been traveling in all directions from every point in space. The light that left the most distant observable regions did so very early in the universe's history. In some cases, within the first few 100 million years of its existence. That light has been crossing space ever since, and it is only now arriving at our telescopes. But here is where the picture becomes more layered. Space itself has been expanding throughout that entire journey. The regions of space that emitted the oldest light we can detect were not, at the time of the mission, as far away as they are today. They were much closer. Over billions of years, the expansion of space carried them outward, away from us, even as their light continued traveling in our direction. By the time that light arrives, the source is vastly more distant than the light travel distance alone would suggest. Consider what this means in practical terms. The most distant light we can detect, the cosmic microwave background radiation, a faint glow left over from the early universe, was emitted when the universe was only about 380,000 years old. At that time, the regions emitting that light were approximately 42 million light years away from what would eventually become our location. Today, those same regions are approximately 46 billion light years away. The light has traveled 13.8 billion light years to reach us, but the source is now 46 billion light years distant. This is not a contradiction. It is simply what happens when the fabric of space expands during the journey of light across it. The light travels at a fixed speed through local space, but the space itself is stretching, carrying distant objects further away, even as their emitted light moves toward us. Understanding this helps clarify what we mean when we talk about the size of the observable universe. When astronomers say, the observable universe has a radius of approximately 46 billion light years, they are describing the current distance to the most remote objects whose light has reached us. They are not saying that light has traveled 46 billion light years. The light travel distance is 13.8 billion light years. The difference between those two numbers is entirely accounted for by the expansion of space. This also helps explain something that might otherwise seem puzzling. If the universe is only 13.8 billion years old, how can we see anything that is farther than 13.8 billion light years away? The answer is that the objects we observe were much closer when they emitted their light. Space has since carried them further away. There is no violation of the speed of light here. Nothing moved faster than light through space. It is space itself that expanded, carrying objects with it. Light, then, is both our greatest tool and our fundamental limitation. It is the only messenger we have from distant parts of the universe. Every piece of information we possess about objects beyond our solar system arrived here in the form of electromagnetic radiation. Visible light, radio waves, infrared, X-rays, and other forms of light traveling across space at the same universal speed. Without that light, those objects would be completely unknowable to us. And this is precisely why a horizon exists. Light travels fast, but not infinitely fast. The universe has existed for a finite amount of time. Those two facts together create a limit. There will always be regions of space from which light has not yet had time to reach us. As the universe ages, light from slightly more distant regions will eventually arrive, expanding our observable sphere incrementally. But the expansion of space works against this process. Beyond a certain distance, space is expanding so rapidly that light from those regions will never close the gap. Those regions are receding faster than their light can travel toward us. This is the edge, not a wall, not an end, but a horizon. The point beyond which light will never arrive, no matter how long we wait. Everything on the far side of that horizon exists in permanent darkness from our perspective. The universe out there is real. It is governed by the same physics. It contains matter, energy, and structure. But it is separated from us by a boundary that no signal, no particle, and no information of any kind can ever cross in our direction. We will spend much of tonight's journey examining that boundary from different angles. What creates it? What lies beyond it? And what it means for our understanding of the cosmos. But first, we will look more closely at the horizon itself and at the remarkable fact that it has a precise and calculable location. Chapter 3. The Cosmic Horizon. Every observer in the universe has a horizon. It does not matter where you are located, in the Milky Way, in a distant galaxy cluster, in a region of space billions of light years from here. From any point in the universe, there exists a sphere of observable space centered on that point, and beyond that sphere, a region of permanent invisibility. The horizon is not a feature of any particular location. It is a feature of the universe itself, arising from the combination of a finite speed of light, a finite age, and an expanding fabric of space. We call this the cosmic horizon, or sometimes the particle horizon. It marks the boundary between the region of space that has been able to exchange light with us since the beginning of the universe, and the region that has not. Everything inside our horizon has, at some point in cosmic history, been in potential communication with us through light. Everything outside it has not. The two regions are causally disconnected, meaning that no event in one region has ever been able to influence the other through any signal traveling at or below the speed of light. This causal disconnection is one of the most significant facts about the structure of the universe. It means that the universe we observe is not the whole universe. It is a sample, a finite, bounded, observable portion of something that may extend far beyond what we can ever detect. The cosmic horizon is the edge of our sample. Beyond it, the experiment continues, but we have no access to the results. The location of our cosmic horizon is not arbitrary. It can be calculated with precision using our best understanding of the universe's age, expansion rate, and composition. The current consensus places the particle horizon at a comoving distance of approximately 46 billion light-years in every direction. This gives the observable universe a diameter of roughly 93 billion light-years, an almost incomprehensibly large volume of space containing an estimated 2 trillion galaxies, each home to hundreds of billions of stars. And yet, this entire vast structure, 2 trillion galaxies, hundreds of billions of stars each, spread across 93 billion light-years, is only the observable portion. The full universe, if it is finite, is larger. If it is infinite, our observable portion is an infinitely small fraction of the whole. Either way, the cosmic horizon reminds us that our view of the universe is fundamentally limited, not by technology, but by physics itself. It is worth pausing here to appreciate what this means. Human beings have built instruments of extraordinary sensitivity. We have placed telescopes in orbit above the atmosphere. We have detected gravitational waves from colliding black holes more than 1 billion light-years away. We have captured light from galaxies that existed when the universe was only a few 100 million years old. Our observational reach is genuinely remarkable. And still, the cosmic horizon sits at a distance we cannot cross, enforced by rules that no engineering advance will ever circumvent. The horizon is not a technological problem. It is a geometric and physical one. The universe has existed for a finite time. Light travels at a finite speed. Space expands at a rate that, beyond a certain distance, outpaces the speed of light. These three facts together create a boundary that is as real and as permanent as any physical structure in nature. There is something quietly humbling about this. We are surrounded, in every direction, by a universe we cannot see. Our instruments point outward and gather light from billions of galaxies, and still we are looking at only a fraction of what exists. The rest is beyond the horizon, inaccessible not because we haven't tried hard enough, but because the universe is structured in a way that makes that access impossible. The cosmic horizon also has an important twin, the event horizon. While the particle horizon marks the boundary of everything that has ever been able to send us a signal, the event horizon marks the boundary of everything that will ever be able to send us a signal in the future. Due to the accelerating expansion of the universe, the event horizon is actually closer than the particle horizon. There are galaxies we can currently observe, galaxies whose ancient light is reaching us right now, that we will never be able to observe again in the future. Their light is still arriving from the past, but new light they emit today will never reach us. They are already, in a meaningful sense, beyond our future reach. This is one of the stranger consequences of living in an accelerating universe. The observable universe is not a stable, fixed region. It is dynamic. Over immense timescales, galaxies near the edge of our observable sphere will fade from view as the expansion of space carries them beyond our event horizon. The night sky, billions of years from now, will be a quieter and emptier place, not because the universe has ended, but because more and more of it will have slipped permanently beyond the boundary of what can be seen. For now, we inhabit a moment in cosmic history when the observable universe is rich with structure. Galaxies cluster into filaments and sheets. Light from the early universe still reaches us. The cosmic microwave background remains faintly detectable in every direction. We are, in some sense, fortunate observers, living at a time when the universe is still generously visible, but the horizon is always there. In every direction, at a distance of 46 billion light-years, the observable universe ends. Beyond it, the cosmos continues, silent, invisible, and permanent. Chapter 4. What the universe is made of at its limits. As we move outward from our own galaxy toward the edge of the observable universe, the universe does not become simpler. It becomes, in certain ways, more uniform. But the structures embedded within that uniformity are vast, beyond easy description. To understand what exists near the limits of what we can observe, it helps to first understand how matter is arranged across cosmic scales, and how that arrangement changes as we look further and further back in time. On the smaller scales relevant to cosmology, matter clumps into stars. Stars gather into galaxies. Galaxies range enormously in size and shape, from small irregular collections of a few billion stars to massive elliptical galaxies containing several trillion. Our own Milky Way sits somewhere in the middle of this range, a barred spiral galaxy of perhaps 300 billion stars, orbited by dozens of smaller satellite galaxies and embedded within a much larger halo of dark matter. Galaxies rarely exist in isolation. They gather into groups and clusters, bound together by gravity. Our Milky Way belongs to a small collection called the Local Group, which contains more than 50 galaxies, the largest of which are the Milky Way and the Andromeda Galaxy. The Local Group is itself a relatively modest structure by cosmic standards, a quiet corner of a much larger arrangement. Beyond the Local Group, galaxy clusters grow larger and more populous. The Virgo cluster, the nearest large galaxy cluster to us, contains more than 1,000 galaxies and sits approximately 54 million light-years away. The Perseus cluster, further still, contains thousands of galaxies embedded in an enormous cloud of superheated gas. These clusters are among the most massive gravitationally bound structures in the universe, containing more mass in hot gas alone than in all their stars combined. But even galaxy clusters are not the largest structures in the universe. Clusters themselves gather into superclusters, extended regions of space where the density of galaxies is higher than average. Our Local Group belongs to the Laniakea supercluster, a vast structure 500 million light-years across, containing the mass of approximately 100 million billion suns. Laniakea was only fully mapped in 2014, when astronomers traced the gravitational flow of galaxies across a large region of space and identified the boundaries of this enormous structure for the first time. And yet, even superclusters are not the end of the hierarchy. At the largest scales, the universe is organized into a structure known as the cosmic web, a network of filaments, sheets, and nodes separated by enormous empty regions called voids. The filaments are long threads of galaxies and dark matter stretching across hundreds of millions of light-years. The sheets are flattened concentrations of matter where filaments intersect. The nodes, where multiple filaments meet, are the locations of the largest galaxy clusters, and between all of this structure lie the voids, regions of space that are nearly empty, spanning hundreds of millions of light-years in every direction. This cosmic web is the large-scale skeleton of the observable universe. It was not placed there arbitrarily. It grew from tiny fluctuations in the density of matter that existed in the earliest moments of the universe. Fluctuations so small they were barely detectable, but large enough to serve as seeds around which gravity could slowly draw matter together over billions of years. The universe we see today, with all its filaments and clusters and voids, is the result of that slow gravitational assembly process, playing out across the full age of cosmic time. As we look toward the edge of the observable universe, we are looking back toward the time when this assembly process was still in its early stages. The most distant galaxies we can observe are young, balmed, formed when the universe was only a few 100 million to a few billion years old. They are smaller and less organized than the galaxies we see nearby. They are forming stars at extraordinary rates, burning brightly in the early universe before settling into the more measured pace of older, more mature galaxies. In some ways, they are unrecognizable compared to the galaxies of the present-day universe. This is one of the great revelations of deep sky observation. When we look at the edge of the observable universe, we are not seeing a distant version of the present. We are seeing the past, a universe in an earlier state, before the structures we are familiar with had fully formed. The cosmic web was less developed. Galaxy clusters were smaller and less concentrated. The universe was denser, hotter, and more active with star formation. The James Webb Space Telescope, launched in December of 2021, has allowed us to peer deeper into this early universe than ever before. It has detected galaxies existing within the first few 100 million years of cosmic history. Galaxies that are surprisingly large and well-formed for their age, challenging some of our models of how quickly structure can develop in the early universe. Each new observation from Webb pushes our understanding of cosmic evolution a little further, filling in the picture of what the universe looked like as it approached its current form. But there is a limit even to what Webb can show us. At a certain point, the universe becomes opaque to visible and infrared light. In the period before the first stars formed, a period astronomers call the Cosmic Dark Ages, the universe was filled with a fog of neutral hydrogen gas that absorbed light rather than transmitting it. Light from that era cannot reach us in its original form. The earliest direct light we can observe is the cosmic microwave background, emitted when the universe was 380,000 years old and the fog of hydrogen finally cleared. Everything before that moment is hidden behind a wall of opacity. And beyond the cosmic horizon, everything is hidden behind a wall of distance and expansion. Between these two barriers, one in time, one in space, lies the full extent of the observable universe, rich, structured, and ancient, and still only a fraction of what exists. Chapter 5. The expansion of space. The universe is expanding. This is one of the most well-established facts in all of modern cosmology, and one of the most difficult to hold in the mind comfortably. It does not mean that galaxies are flying outward through space like fragments from an explosion. It means that space itself, the fabric in which galaxies are embedded, is stretching. The distance between galaxy clusters is increasing, not because those clusters are moving through space, but because the space between them is growing. This distinction matters enormously. When we say that a galaxy 1 billion light-years away is receding from us, we do not mean that it is traveling through space in the way a rocket travels through space. We mean that the space between us and that galaxy is expanding, adding distance between us even if the galaxy itself has no particular velocity relative to its local surroundings. The galaxy is, in a sense, being carried away from us by the growth of space itself. The expansion of the universe was first observationally confirmed in the 1920s, when astronomer Edwin Hubble demonstrated that distant galaxies were receding from us, and that the further away a galaxy was, the faster it appeared to be receding. This relationship, known as Hubble's law, was the first direct evidence that the universe was not static, but dynamic and growing. The rate of that expansion is described by a value called the Hubble constant, which relates the recession speed of a galaxy to its distance from us. For decades after Hubble's discovery, cosmologists assumed that the expansion of the universe must be slowing down. Gravity, acting across cosmic distances, should pull matter together and gradually break the outward expansion set in motion by the Big Bang. The universe was expected to be decelerating. The only question was whether it would eventually halt and reverse, collapsing back into a final contraction, or whether it would continue expanding forever at a diminishing rate. In 1998, two independent research teams studying distant supernovae made a discovery that overturned this assumption entirely. Instead of slowing down, the expansion of the universe was speeding up. The rate of expansion was accelerating. Something was pushing space apart with increasing force, working against the pull of gravity on the largest scales. That something was given the name dark energy, a label that describes our observations without explaining their cause. Dark energy remains one of the deepest unsolved problems in physics. We know it exists because of what it does. We do not know what it is. The acceleration of cosmic expansion has direct consequences for the cosmic horizon. In a universe that was expanding but decelerating, the observable universe would grow over time. Light from progressively more distant regions would eventually reach us as the universe aged. In an accelerating universe, the situation is more complex and in some ways more final. Beyond a certain distance, space is expanding so rapidly that light emitted today from those regions will never reach us. The expansion will carry those regions away faster than their light can travel toward us. This critical distance, the boundary beyond which light emitted today will never arrive, is called the cosmological event horizon. It sits at a distance of approximately 16 billion light-years from us. Everything beyond that distance is already, in terms of future communication, permanently out of reach. We may still be receiving ancient light from regions beyond the event horizon, light emitted long ago when those regions were closer. But no new information from those regions will ever arrive. The event horizon is therefore shrinking in a meaningful sense, not in physical size, but in terms of what it encompasses. Galaxies that are currently just inside our event horizon will eventually be carried beyond it by the accelerating expansion. Over time, the population of galaxies from which we can receive new signals will decrease. The universe will not end, but our observable slice of it will gradually empty of newcomers. On very long timescales, trillions of years into the future, the night sky of any civilization that might exist will look very different from ours. Nearly all the galaxies visible to us today will have receded beyond the event horizon. Only the galaxies gravitationally bound to our own local group, those close enough that gravity overcomes the expansion, will remain visible. The rest of the universe will have effectively vanished from view, not destroyed, but simply carried beyond the boundary of what can be seen. This is a remarkable conclusion. The universe may be in a temporary state of unusual visibility. We exist at a time when the cosmic web is still richly observable, when the light from billions of galaxies fills our telescopes, when the cosmic microwave background is still detectable as a faint whisper in every direction. Future observers, if they exist, may have no way of knowing that the universe extends beyond their local galaxy group. The evidence will have receded beyond their horizon. They may look out at a quiet, nearly empty sky and conclude, incorrectly, that their galaxy is all there is. We are, in this sense, fortunate. We exist at a moment when the universe is still telling its own story to anyone equipped to listen. The expansion has not yet silenced the distant voices. The light is still arriving. The horizon is still filled with ancient signals from across the full breadth of cosmic history. But the expansion continues, and beyond a certain boundary, it has already won. Space is growing faster than light can follow, and the darkness beyond our horizon is not the darkness of emptiness. It is the darkness of distance, a universe full of matter and energy and structure, separated from us by the one barrier that cannot be overcome. Chapter 6. Galaxies we will never reach. There are galaxies we can see tonight that we will never be able to reach. Not in the practical sense. The distances involved are so vast that no civilization could reasonably contemplate traveling them. But in a deeper, more fundamental sense, there are galaxies whose light is currently arriving at our telescopes, galaxies we can observe and study and catalogue that are already beyond our cosmological event horizon. No signal we send today will ever reach them. No future spacecraft, traveling at any speed below the speed of light, will ever close the distance. They are visible to us, but permanently beyond our reach in every meaningful physical sense. This is one of the stranger aspects of living in an accelerating universe. Visibility and accessibility are not the same thing. A galaxy can be observable, its ancient light still crossing the shrinking gap between us, while simultaneously being unreachable, already carried beyond the boundary from which future communication is possible. We are seeing its past. Its present is already lost to us. To understand which galaxies fall into this category, it helps to distinguish clearly between two different horizons. The particle horizon, as we discussed earlier, marks the boundary of everything whose light has ever had time to reach us. The full extent of the observable universe, approximately 46 billion light-years in radius. The cosmological event horizon marks the boundary of everything from which we can still receive future signals, currently sitting at approximately 16 billion light-years. The gap between these two distances, roughly 30 billion light-years in radius, contains galaxies we can observe but never contact. Their ancient light still reaches us. Their present and future are permanently beyond our access. Within that gap lie an enormous number of galaxies. The observable universe contains an estimated 2 trillion galaxies in total. A significant fraction of those galaxies are already beyond our event horizon. We can study them. We can measure their redshifts, analyze their compositions, map their structures. But we are studying fossils, light that left those galaxies billions of years ago, before they crossed beyond our future reach. The galaxies closest to our event horizon present a particularly poignant picture. Their light arrives at our telescopes having been stretched enormously by the expansion of space during its long journey. This stretching shifts the light toward the red end of the spectrum, a phenomenon called cosmological redshift. The more distant the galaxy, the greater its redshift. Galaxies near the edge of the observable universe have redshifts so extreme that their light, originally emitted as ultraviolet or visible radiation, arrives at Earth as infrared or even microwave radiation. Without instruments sensitive to these longer wavelengths, those galaxies would be entirely invisible to us. The James Webb Space Telescope was designed in part to observe these highly redshifted galaxies, to detect the infrared light of the early universe that older telescopes could not capture. Since its first observations in 2022, it has identified galaxies at redshifts that place them within the first few 100 million years of cosmic history. These are among the most distant objects ever observed, existing at the very edge of what light and time permit us to see. But even Webb has a limit. There is a redshift beyond which galaxies become undetectable, not because our instruments are insufficiently sensitive, but because the light from those regions was emitted before the universe became transparent. Before the cosmic dark ages ended and the first stars ignited, there were no sources of light to emit signals we could detect. The universe before that era is, in terms of direct observation, permanently dark. Beyond the galaxies Webb can see, Beyond the redshift limit of any optical or infrared instrument lies the cosmic microwave background, the oldest light in the observable universe, emitted 380,000 years after the Big Bang. It is the final layer of the observable universe, a shell of ancient light surrounding us in every direction. Beyond that shell, our direct observational access ends entirely. What lies beyond that shell, in the unobservable universe, we can only infer. We have strong theoretical reasons to believe the universe continues beyond the cosmic microwave background, that the same laws of physics apply, that matter and energy are distributed in broadly similar ways, and that the cosmic web of filaments and voids extends far beyond what we can see. But we cannot confirm this observationally. The inference is based on our models, not our measurements. The galaxies we will never reach are a reminder that the universe does not owe us access to its full extent. It operates according to rules that happen in our era, to permit a remarkable degree of observation. But those same rules impose limits that are absolute and permanent. The expansion of space is not a problem to be solved or an obstacle to be overcome. It is a feature of the universe's structure, as fundamental as the speed of light or the laws of thermodynamics. There is something worth sitting with in that. The galaxies beyond our event horizon are real. They contain stars and likely planets, and perhaps structures and phenomena we have not yet imagined. They evolve and age and change according to the same physics that governs our own galaxy, and we will never know what they become, not because we lack the tools, but because the universe is simply too large and expanding too fast for any signal to carry that information to us. The darkness beyond our horizon is not empty. It is full. It is simply unreachable. Chapter 7. What lies in the darkness? Beyond the cosmic horizon, the universe continues. This is not a speculative claim. It is a straightforward consequence of our best physical models, supported by everything we know about the geometry and composition of the cosmos. The observable universe is not the whole universe. It is a window, a finite bounded region of something that extends, in all likelihood, enormously further in every direction. What lies beyond that window is not nothing. It is more universe. The question is how much more. And here, the honest answer is that we do not know. We cannot measure the full extent of the universe directly. We cannot send signals beyond our horizon and wait for them to return. We cannot observe the curvature of space on scales large enough to determine whether the universe is finite or infinite. What we can do is reason carefully from what we do know, and consider what our best models imply about the territory beyond our view. Our current understanding of cosmology is built on a framework called the Standard Model of Cosmology, sometimes referred to as the lambda-CDM model. This model describes a universe composed of ordinary matter, dark matter, and dark energy, governed by the equations of general relativity and originating in a hot, dense state approximately 13.8 billion years ago. Within this framework, the universe appears to be geometrically flat, meaning that parallel lines do not converge or diverge over cosmic distances, and the overall curvature of space is, to the best of our measurement, zero. A geometrically flat universe has significant implications for its size. In a positively curved universe, one that curves back on itself like the surface of a sphere, space would be finite, and the universe would have a finite volume even without an edge. In a negatively curved universe, space would be infinite. In a flat universe, the geometry also implies infinite extent, unless there is some additional topological feature that causes space to wrap around on itself at a scale larger than our observable sphere. Our best measurements suggest the universe is flat to within a very small margin of error. If it is truly flat and not topologically closed, it is infinite. An infinite universe would contain an infinite amount of matter, an infinite number of galaxies, and, given the probabilistic nature of quantum events, an infinite number of regions that are statistically identical to our own observable universe. Every possible arrangement of matter would exist somewhere, repeated infinitely many times across an infinite expanse of space. This is a conclusion that is difficult to absorb. It follows logically from the combination of an infinite flat universe and the probabilistic nature of physical processes, but it sits uneasily with everyday intuition. We are not required to believe it. It is a theoretical consequence, not a confirmed observation. But it is what our best models imply, and it is worth holding carefully in mind as we consider what lies beyond our horizon. Even setting aside the question of infinity, the unobservable universe is almost certainly vast beyond any practical meaning of the word. Various estimates, based on the observed flatness of space and the properties of cosmic inflation, suggest that the full universe may be at least 10 to the power of 23 times larger than the observable universe. A number so large it resists any intuitive comparison. Others place the estimate far higher. The observable universe, with its 2 trillion galaxies and its 93 billion light-year diameter, may be an almost negligibly small fraction of the whole. Beyond our horizon, the same physical processes that shaped our observable universe almost certainly continue to operate. Dark matter halos collapsed under gravity. Baryonic matter fell into those halos and formed galaxies. Stars ignited, lived out their lives, and seeded the surrounding gas with heavier elements. Planetary systems formed. The cosmic web of filaments and voids extended across scales we cannot observe. All of this happened, is happening, in regions of space that we will never see. There is also the matter of cosmic inflation to consider. Inflation is the theorized period of extraordinarily rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. During inflation, a region of space far smaller than an atomic nucleus expanded to a size larger than the observable universe today, in an almost incomprehensibly brief interval of time. Inflation, if it occurred as theorized, would have stretched the universe to enormous size, far larger than our observable sphere, and would have smoothed out any large-scale curvature, producing the flat geometry we observe today. Inflation also has implications for what the unobservable universe might look like. In many versions of inflationary theory, inflation did not end uniformly everywhere. Different regions of space exited the inflationary period at different times, producing what some theorists call a multiverse. A vast collection of regions, each with its own post-inflationary history, potentially governed by different physical constants or different arrangements of matter and energy. This is a deeply speculative area of physics, and it remains far beyond our ability to test observationally. But it illustrates how the question of what lies beyond our horizon connects to some of the deepest and most unsettled questions in theoretical physics. What we can say with confidence is this: beyond our cosmic horizon, space continues, matter continues. The laws of physics, as best we can determine, continue. The darkness beyond our observable sphere is not a void. It is not an absence. It is a continuation of the same universe we inhabit, governed by the same rules, filled with the same kinds of structures, simply located beyond the boundary that light and time have drawn around our view. We cannot see it. We cannot reach it. We cannot communicate with it, but it is there. Chapter 8: The Universe Beyond the Visible. We have spent considerable time examining the boundary of the observable universe, what creates it, where it sits, and what it means for our ability to gather information about the cosmos. Now it is worth turning our attention more deliberately to what lies on the other side of that boundary, not in speculative terms, but in terms of what our best physical understanding actually permits us to say about the unobservable universe and its relationship to the region we can see. The first thing to establish is that the unobservable universe is not qualitatively different from the observable one. There is no reason, within our current understanding of physics, to suppose that the laws of nature change beyond our horizon. The speed of light is the same. Gravity operates the same way. Atoms form from the same particles and behave according to the same rules. The cosmic web of filaments and voids almost certainly continues beyond our horizon in, broadly, the same pattern we observe within it. The unobservable universe is not exotic or alien. It is simply more of the same universe, located beyond the distance that light and time permit us to see. This continuity is itself a remarkable inference. We are reasoning about a region we cannot observe, using physical laws derived entirely from observations within our horizon, and concluding that those laws apply uniformly across a domain that may be vastly larger than anything we can detect. This is not a guess. It is grounded in the internal consistency of our physical models and in the observed uniformity of the universe at large scales. But it is worth acknowledging that it is an extrapolation, a confident one, but an extrapolation nonetheless. Within the observable universe, the distribution of matter is remarkably uniform when viewed at the larger scales. Individual galaxies, clusters, and superclusters create variation at smaller scales, but averaged across volumes of space larger than a few 100 million light-years, the density of matter is consistent in every direction we look. This uniformity, called the cosmological principle, is one of the foundational assumptions of modern cosmology. It states that the universe is, on large scales, both homogeneous and isotropic. Homogeneous means that it looks the same from any location. Isotropic means that it looks the same in every direction. If the cosmological principle holds beyond our horizon, and our models strongly suggest it does, then the unobservable universe resembles the observable one in its broad statistical properties. Galaxy clusters form at the nodes of filaments. Voids separate regions of higher density. The same proportions of ordinary matter, and dark energy govern the overall dynamics of space. The universe beyond our horizon is not a fundamentally different place. It is a continuation of the landscape we already know. There is, however, one important caveat. The cosmological principle is a statistical statement. It describes averages over large volumes, not individual locations. Within those averages, enormous variety is possible. Our own observable universe contains regions that differ dramatically from one another. Dense galaxy clusters, vast empty voids, quiet backwaters like our own local group, and active regions of intense star formation. The unobservable universe almost certainly contains the same range of variation, and perhaps structures and configurations that happen not to exist within our observable sphere simply due to the finite size of our sample. It is also worth considering what the unobservable universe looked like in the past. Because we observe distant regions of the observable universe as they existed in the past, due to the finite travel time of light, we have a record of how the universe evolved over time within our horizon. The unobservable universe underwent the same evolutionary history. It emerged from the same hot, dense early state. It passed through the same epochs, the quark epoch, the formation of protons and neutrons, the synthesis of light elements, the recombination era when the cosmic microwave background was released, the cosmic dark ages, the epoch of reionization when the first stars ignited, and the long subsequent era of galaxy formation and evolution. All of this happened beyond our horizon, just as it happened within it. The unobservable universe has a history as rich and as long as our own. It simply unfolded beyond the boundary of our sight. One of the more thought-provoking implications of a large unobservable universe concerns the question of uniqueness. Within our observable universe, the arrangement of matter is specific and particular. A unique configuration of galaxies, clusters, voids, and structures that formed from a specific set of initial conditions. If the full universe is vastly larger than our observable sphere, and if the initial conditions varied randomly across that larger volume, then statistically, somewhere in the unobservable universe, there exist regions whose matter distribution closely resembles our own. In an infinite universe, the match would be exact. Every possible configuration of matter, including one identical to our observable universe, would exist somewhere. This is not mysticism or science fiction. It is a straightforward consequence of probability applied to large numbers. If the universe is large enough and the initial conditions varied randomly, repetition becomes not just possible, but inevitable. The unobservable universe may contain, somewhere in its vastness, a region indistinguishable from the one we inhabit. We have no way of knowing. We have no way of ever knowing. But the mathematics does not forbid it. For now, we hold this thought lightly and move on. The universe beyond the visible is real, continuous with our own, and governed by the same physics. It is simply and permanently beyond our reach. Chapter 9. Why light from there will never arrive. We have established that the universe extends beyond our cosmic horizon, and that the region beyond it contains matter, structure, and history broadly similar to our own. We have also noted, in passing, that light from those regions will never reach us. Now it is worth examining that conclusion more carefully, not simply as a fact to be accepted, but as a physical process to be understood. Why precisely will that light never arrive? What is it about the structure of an expanding universe that creates a permanent barrier between us and the regions beyond our horizon? The answer begins with the relationship between distance and the speed of light. Light travels at approximately 299,000 kilometers per second through empty space. This is fast by any everyday standard, but it is a finite speed. In a static universe, one that neither expands nor contracts, light emitted from any location would eventually reach any other location, given enough time. Distance would delay the arrival of light, but it would not prevent it. In a static universe, there would be no horizon. The universe is not static, it is expanding, and that expansion changes the calculation fundamentally. As light travels through space toward us, the space it is traveling through is itself stretching. Every moment, the distance between the source of the light and our location increases, not because either is moving through space, but because space is growing between them. The light must cover not just the original distance, but the additional distance created by expansion during its journey. For light emitted from regions within a certain distance, this is not a problem. The expansion adds distance, but the light is close enough that it can outpace the growth and eventually arrive. For light emitted from regions beyond a critical distance, the cosmological event horizon, the expansion adds distance faster than the light can cover it. The light makes progress, but the gap grows faster than the progress. The light will never close the distance. It will travel forever through an expanding universe, always approaching but never arriving. This is not a gradual fading. It is a hard physical limit. There is a specific distance, currently approximately 16 billion light years, beyond which light emitted today will never reach us, regardless of how long we wait. Light from sources beyond that distance is permanently prevented from arriving, not by any barrier or obstruction, but simply by the geometry of an accelerating, expanding space. It is worth being precise about what accelerating expansion means in this context. The expansion of the universe is not just continuing, it is speeding up. The rate at which space grows between distant objects is increasing over time, driven by dark energy. This acceleration means that the cosmological event horizon is not receding from us at a constant rate. It is, in a sense, closing in, not physically, but in terms of what it encompasses. Objects that are today just inside the event horizon will eventually be carried beyond it by the accelerating expansion. Future light they emit will no longer be able to reach us. This process has already been underway for billions of years. Many of the galaxies visible in our deepest telescope images are already beyond our event horizon in terms of future communication. Their ancient light, emitted long ago when they were closer, is still arriving. But any signal they emit today, any light, any gravitational wave, any particle, will never reach us. The expansion has already won that race. There is a subtlety here worth dwelling on. The fact that light from beyond the horizon will never arrive does not mean that the sources of that light are moving away from us faster than light in a local sense. In the immediate vicinity of any point in space, the laws of special relativity hold. Nothing moves through space faster than light. The recession of distant galaxies is not motion through space. It is the expansion of space itself, which is not subject to the same speed limit. Space can expand at any rate. It is the expansion of the medium, not the motion of objects within it, that creates the horizon. This distinction is subtle but important. The galaxies beyond our horizon are not violating any physical law. They are not traveling faster than light. They are simply embedded in a region of space that is expanding rapidly enough that light cannot bridge the growing gap. The limit is geometric, not kinetic. As the universe continues to age and the expansion continues to accelerate, the event horizon will encompass fewer and fewer sources of future signals. Galaxies that are today marginally within our event horizon will gradually be carried beyond it. The population of the universe that can communicate with us will shrink. On timescales of tens of billions of years, only the galaxies gravitationally bound to our local group, close enough that gravity overcomes the expansion, will remain within reach. The rest of the universe will have passed beyond the horizon of future contact, their signals permanently outpaced by the growth of space between us. The light from those regions is already on its way, in some cases. Ancient photons emitted billions of years ago by galaxies now beyond our event horizon are still crossing the universe toward us, making their slow progress through expanding space. Some of them will arrive. Others, emitted from sources already too distant, will not. They will travel forever, carried along by an expanding universe, never reaching a destination. There is something quietly melancholy in that image. Light traveling through the dark, crossing distances measured in billions of light years, moving toward a destination it will never reach. Not lost exactly, still real, still carrying information, still moving at the speed of light through local space, simply overtaken by the universe's expansion in a race that was already lost before it began. Chapter 10. What we can never know. there is a particular kind of limit that science rarely confronts directly. Most limitations in scientific knowledge are practical. We lack the instruments, the funding, the computational power, or the time to answer a given question. These are limitations of capability, and in principle they can be overcome. Given better tools and more resources, we could answer questions that are currently beyond our reach. The history of science is largely a story of practical limits being pushed back, one discovery at a time. The cosmic horizon represents a different category of limit entirely. It is not a practical limitation. It is a fundamental one, built into the structure of the universe itself, enforced by the speed of light and the geometry of expanding space. No improvement in technology will ever allow us to observe what lies beyond our horizon. No telescope, however sensitive, will detect light from regions where the expansion of space prevents that light from arriving. The limit is not an engineering problem. It is a physical law. This places certain questions permanently beyond the reach of empirical science. We cannot observe the full extent of the universe. We cannot determine, through direct measurement, whether the universe is finite or infinite. We cannot confirm whether the cosmological principle holds beyond our horizon, whether the unobservable universe truly resembles the observable one in its broad properties. We cannot detect whether other regions of space underwent different inflationary histories, or whether the physical constants we measure locally are universal or merely local features of our particular region. These are not small questions. They are among the most fundamental questions we can ask about the nature of reality. And the honest answer, given what physics tells us about our horizon, is that we may never be able to answer them through observation. We can reason about them. We can construct mathematical models that address them. We can identify which answers are consistent with the physics we know. But we cannot test those answers against direct evidence from beyond the horizon, because that evidence cannot reach us. This is a significant philosophical boundary. Science, as a method, is grounded in observation and testability. A hypothesis that cannot in principle be tested, even in an idealized sense, sits outside the domain where science can render a verdict. The question of what lies beyond the cosmic horizon is not, in the strictest sense, a scientific question. It is a question that science can inform, but not definitively answer. Some physicists are comfortable with this. They argue that our models are well constrained within the observable universe, and that their implications for the unobservable universe are reliable extensions of well-tested physics. Others are more cautious, drawing a firm line between what can be observed and what must remain in the domain of theory and inference. Both positions are intellectually defensible. The tension between them reflects a genuine and unresolved question about the boundaries of scientific knowledge. What we can know, and know well, is the observable universe itself. Within our horizon, the tools of modern astronomy and cosmology have produced a remarkably detailed picture of the cosmos. We know the age of the universe to within a small margin of error. We know its composition, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. We know the large-scale structure of the cosmic web. We have mapped the distribution of galaxies across billions of light years. We have detected the faint afterglow of the Big Bang in every direction. We have observed the formation of the first galaxies and traced the evolution of cosmic structure across 13 billion years of history. This is an extraordinary body of knowledge, accumulated over less than a century of modern cosmology. It is grounded in observation, tested against multiple independent lines of evidence, and refined continuously as new data arrives. Within the observable universe, science has achieved something genuinely remarkable. But the observable universe is bounded, and beyond that boundary, knowledge gives way to inference, and inference gives way to silence. We can say what we expect to find beyond the horizon, based on the physics we know. We cannot confirm it. The confirmation is permanently out of reach, carried away by the same expansion that created the horizon in the first place. There is a certain intellectual honesty required in sitting with this. It is tempting to fill the unknown with speculation, to populate the unobservable universe with exotic structures, alternate physical laws, or parallel histories. Some of this speculation is grounded in serious theoretical work. Some of it is less rigorous. The difficulty is that, beyond the horizon, the tools that allow us to distinguish between well-grounded theory and unconstrained speculation are unavailable. We cannot observe our way to an answer. What remains, then, is a clear-eyed acknowledgement of the boundary. The universe is larger than we can see. The portion we cannot see is governed, in all likelihood, by the same physics as the portion we can. Beyond that, we hold our conclusions lightly, and we resist the temptation to claim more certainty than the evidence warrants. This is not a failure of science. It is science functioning exactly as it should, following the evidence to its limits, acknowledging where those limits lie, and maintaining honesty about what lies beyond them. The cosmic horizon is not an embarrassment. It is a precise and well-understood feature of the universe we inhabit. Knowing exactly what we cannot know is itself a form of knowledge, and not a trivial one. Chapter 11. The Scale of What is Hidden. We have spent this evening moving carefully through the observable universe, its structure, its limits, and the physics that creates those limits. We have considered what lies beyond our horizon, and why it remains permanently out of reach. Now it is worth pausing to consider the scale of what is hidden, not in abstract terms, but as concretely as our current understanding permits. How much universe lies beyond our horizon? How does the unobservable portion compare to the portion we can see? And what does that comparison tell us about our place in the larger cosmos? The observable universe is large beyond any intuitive grasp. Its diameter of 93 billion light-years encompasses a volume of space containing an estimated 2 trillion galaxies. Each of those galaxies contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is estimated at somewhere around 200 sextillion, a 2 followed by 23 zeros. The total number of planets is likely higher still. By any everyday measure, the observable universe is incomprehensibly vast, and yet, by the best estimates available to us, it may represent an almost negligibly small fraction of the full universe. The reasoning behind this conclusion draws on several lines of evidence and theory. The most direct comes from measurements of the universe's large-scale geometry. As discussed earlier, our best observations indicate that the universe is geometrically flat, that the curvature of space on the largest scales we can measure is indistinguishable from zero. A flat universe, if it has no exotic topological features that cause it to wrap back on itself, is spatially infinite. An infinite universe would make the observable portion not just small, but infinitely small, a finite island in an infinite ocean. Even setting aside the possibility of an infinite universe, the theory of cosmic inflation places strong constraints on the minimum size of the full universe. Inflation predicts that the universe underwent a period of extraordinarily rapid expansion in its earliest moments, stretching space by an enormous factor in an almost inconceivably brief interval. The observable universe we see today represents only a tiny patch of the pre-inflationary region that underwent this stretching. Different inflationary models make different predictions about how large the full universe is relative to our observable sphere, but even conservative estimates place the full universe at many orders of magnitude larger than what we can see. One way to think about this is through the concept of the inflationary expansion factor. During inflation, space expanded by a factor of at least 10 to the power of 26, and in many models, far more. This means that the observable universe, vast as it is, occupies a region that was once fantastically smaller than the full inflated volume. The rest of that volume, the overwhelming majority of it, lies beyond our horizon, expanded beyond our reach, before the universe was even a fraction of a second old. Some estimates, based on specific inflationary models, suggest that the full universe may be at least 10 to the power of 23 times larger than the observable universe in linear scale. In terms of volume, the difference is that number cubed, a figure so large that it renders the observable universe essentially invisible against the full extent of space. Other models suggest even larger ratios. The honest summary is that we do not know how large the full universe is, but our best theoretical frameworks suggest it is vastly, almost incomprehensibly larger than the portion we can observe. What fills all of that space? By the same reasoning that leads us to believe the unobservable universe shares our physics, we expect it to be filled with matter arranged in broadly similar ways. Galaxies, clusters, filaments, voids, the same cosmic web we observe within our horizon, extending across scales we cannot measure. Stars forming and aging and dying. Planetary systems assembling from the debris of stellar evolution. The full range of cosmic structures and phenomena that we have catalogued within our observable sphere, repeated across a volume of space that dwarfs our entire cosmic horizon by factors that have no meaningful everyday analogy. There is also the question of variation. Within the observable universe, we see a wide range of environments, from the densest galaxy clusters to the emptiest voids, from the most active star-forming regions to the quietest elliptical galaxies. The full universe, if it is as large as our models suggest, would contain an even wider range of variation simply by virtue of its size. Regions that differ from our own in ways both subtle and significant. Configurations of matter that happen not to exist within our observable sphere, but are perfectly consistent with the laws of physics. In an infinite universe, every configuration that is physically possible exists somewhere. This is not a statement about parallel universes or alternate realities in any science fiction sense. It is a statement about probability in large numbers. Given enough space and enough random variation in initial conditions, every arrangement of matter that does not violate physical law will occur. The unobservable universe is not just large. It is, if our models are correct, the overwhelming majority of everything that exists. We sit at the center of our observable sphere, surrounded on all sides by a cosmos that extends far beyond what any signal can ever bring to our attention. The 2 trillion galaxies within our horizon are our entire empirical universe, the full extent of what observation can ever tell us. Beyond them, the universe continues in silence, vast and unreachable, indifferent to the boundary our horizon places on our knowledge. The scale of what is hidden is not a cause for despair. It is simply the universe being what it is, larger than any single vantage point can encompass, richer than any single observer can fully know. Chapter 12. A Quiet Boundary. We have traveled a long way tonight. We began at the edge of our own observable sphere, considered the physics that creates it, moved outward through the structures that fill it, and looked as carefully as we could at the darkness beyond. We examined the expansion of space, the recession of galaxies, the permanent silence of regions too distant for their light to ever reach us. We sat with the question of what lies beyond the horizon, and we held the honest answer, that we cannot know for certain, but that our best understanding points to more universe, vast and continuous, extending in every direction beyond the limit of what we can see. It is worth ending not with conclusions, but with reflection. The cosmic horizon is a remarkable thing to contemplate. It is not dramatic. It does not announce itself. There is no visible boundary in the sky, no line where the observable universe ends and the unobservable begins. The horizon is invisible, defined not by any physical structure, but by the relationship between light, time, and the expansion of space. It is everywhere around us and nowhere to be seen. And yet, it is one of the most significant features of the universe we inhabit. It defines the totality of our empirical world. Everything we have ever observed, everything we will ever observe, everything that any instrument we could ever build will ever detect. On one side of the horizon lies all of human knowledge of the cosmos. On the other side lies a universe that is, for all practical purposes, as absent from our experience as if it did not exist at all, even though it almost certainly does, in enormous abundance. There is something deeply human about standing at a boundary and looking outward. We have always done this. Early navigators stood at the edge of known coastlines and looked toward open water. Astronomers of earlier centuries pointed their telescopes at the edge of the visible sky and wondered what lay beyond. Each case, the boundary eventually yielded. New coastlines were mapped, new stars catalogued, new galaxies resolved from what had appeared to be empty sky. The history of human exploration is in large part a history of horizons receding. The cosmic horizon does not recede. It is, in the most literal sense, the final horizon, the one that cannot be pushed back by any instrument, any voyage, any technological advance. It is set by the speed of light and the age of the universe, and it will shift only incrementally as cosmic time continues to pass, and then only inward, as accelerating expansion carries more and more of the universe beyond our future reach. We are not approaching the edge of our observable universe. In terms of what we can ever communicate with, we are slowly losing ground. This is not a melancholy fact, though it can feel like one at first. It is simply the shape of the universe we live in. The cosmos is not obligated to be fully knowable. It is not required to arrange itself so that every region is in principle accessible to every observer. The existence of a horizon is a natural consequence of finite light speed, finite cosmic age, and expanding space. Three features of the universe that are also responsible for much of what makes the cosmos comprehensible and beautiful. The same expansion that creates the horizon also dilutes the early universe's density and allows galaxies to form. The same finite speed of light that limits our view also makes the universe consistent and causally structured. The horizon is not a flaw, it is a feature. What lies beyond it, we have considered carefully. More space, more matter, more galaxies arranged in the familiar architecture of the cosmic web. The same physics, operating across scales we cannot measure, producing structures we cannot observe, across timescales we cannot directly access. The unobservable universe is not mysterious in the sense of being governed by unknown rules. It is mysterious only in the sense of being hidden, present but inaccessible, real but silent. There is a quiet dignity in acknowledging this. Science has taken us an extraordinary distance from our origins as a species puzzling over the lights in the night sky. We have mapped the large-scale structure of the cosmos. We have detected the afterglow of the Big Bang. We have identified the composition of the universe. Ordinary matter, dark energy, and measured the rate of its expansion. We have looked back to within a few 100 million years of the beginning of everything, and we have seen the first galaxies taking shape in the early universe. This is a staggering accumulation of knowledge, built over a few centuries of increasingly precise observation. And at the edge of all that knowledge sits the horizon. Not a wall, not a failure, not an obstacle waiting to be overcome. Just a boundary, quietly marking the limit of what light and time permit us to know. Beyond it, the universe continues, indifferent, enormous, and silent, full of everything our observable sphere contains, repeated and varied across distances that our numbers can describe, but our minds cannot truly hold. We have spent this evening at that boundary, looking outward as carefully as the physics allows. There is nothing more to see from here. The darkness beyond the horizon is complete, and it is permanent, and it is full. If this was a calm place to land tonight, a like or a subscribe helps other wandering minds find their way here.